some of the structure not to keep or maybe introduce new one. And what symplectic geometry does, it's kind of, it retain something related to area form on our two-dimensional surface in high dimension. And then what I want to say is that this is a kind of extremely essential. So when in dimension, in the symplectic topology, I can't explain what I mean. In a sense, topology of manifold of the higher dimensions, the topology become more and more interesting, more and more complicated. And the reason why kind of differential topology is interesting and complicated in dimension 3 and 4 may be related to the fact that at this dimension, these two topologies do not deviate yet too much. They're very close. And then as dimensions become bigger, they're really completely apart. Okay, so anyway, this is a pure philosophy, so let me explain some. So I will kind of start to introduce some symplectic notions, and then we will kind of indicate what they have to do with topology in dimensions 3 and 4. So let's start with symplectic structure. So symplectic structure, I will only need symplectic structure essentially in dimension 4 only. So we have a, but let's start still from dimension 2. In dimension 2, symplectic structure just area form. And you can think that this is a, you can take a just bilinear, skew-symmetric, non-degenerate form, which is just only one form such exists as a determinant. And you can take a globally like differential form. So, and well, any differential 2 form that looks like this with the f, say, if it's non-degenerate, then f is a positive function. And then locally, all forms are equivalent. So you can always, by change of coordinates, you can kill this factor. So essentially, locally, only one form exists. So now you go to dimension 4 and say linear symplectic structure on 4-dimensional form, on 4-dimensional space is a non-degenerate skew-symmetric 2 form. And again, like from the elementary linear algebra, we know that the only one skew-symmetric form on R4 can be written as follows. There's after change of coordinate, we identify this R4 with C2, and then in C2 we have the standard kind of Hermitian product, and then so this is kind of Hermitian complex valued form, and then it has a real part, kind of Euclidean part, and it has a skew-symmetric part, and I don't kind of it has an imaginary part which is a skew-symmetric part. This is a symmetric part of the skew-symmetric, and this is a precisely normal form for the symplectic form or non-degenerate to form. And so in terms of just Euclidean metric, you can write that this omega of p w is equal IV times W. And this is the kind of, I will kind of omit this E, meaning just Euclidean product. So just take a value of the symplectic form of pair of vectors, just you have to multiply one by I and then take a scalar product. So this is a kind of standard. And then again, you can consider at one point, if you want to kind of using exterior algebra, you can write this in the form like x1 wedge y1 plus x2 wedge y2. And if you want to consider this as a kind of differential form, you can write this, put some dx1 wedge dx2, dx2 wedge dy2. And in principle, you can, on 4-dimensional space, you can just consider, just if you take an arbitrary form, not like this one, but arbitrary differential form, differential to form which is non-degenerate, then you have on each tangent space, you may have a kind of different form. Because I in dimension 4 this is not true. And if you have an arbitrary form, if you have a, say, arbitrary form which is a non-degenerate and skew-symmetric, arbitrary differential to form, then the condition that it is locally standard is equivalent to the condition that it's closed by Darboux essentially theorem. And so you can define symplectic structure on four-dimensional space as a closed non-degenerate to form, or equivalently a form which is equivalent to this particular form. So symplectic form manifold is, you can define again either a manifold with this non-degenerate to form, or you can say it just grew out of the Euclidean charts with this form using the map which preserves the form, using symplectic map. So already this definition I somehow mixed in this complex structure into the definition of symplectic form, and this is very useful to kind of to pertain this. Namely, turns out to the following always true. So suppose you have some symplectic, well, again, I'm only talking about form manifold, but it's in fact general fact. Suppose you have any symplectic form manifold, and then you can always find what is called almost complex structure. That means that you can make tangent bundle to be complex line bundle, complex vector bundle. So introduce complex structure on each tangent space, such that on each tangent space this linear symplectic form omega and this complex structure J will be related precisely by this condition. So that means that you can say choose Hermitian metric on our manifold in such a way that that our omega will be imaginary part of this Hermitian metric. So if J is integrable, is a normal complex structure, then this is a precise definition of Kähler-Mann. The existence of such Hermitian form, such that imaginary part is this closed and automatically not degenerate skew-symmetric form. But then it's always the case. So you can always find this J, but not necessarily integrable. So in a sense, symplectic manifold is the same as a kind of almost Kähler manifold. So moreover, choice of such J, of course, not unique, but it's kind of contractible choice. The space of this J, for which this condition is satisfied, is in fact contractible space. So in kind of up to homotopy, you can canonically choose some such J. So I will be kind of always using some J with this omega, and in a sense, my geometry will be very much related to the J, but omega will be like this guard in background. So like maybe even in definition this omega would not appear, but this fact that you have this omega, and essentially the main condition that omega on any complex direction is positive, which is a kind of correlate the fact that this metric is positive definite, is just would be really the major fact which, as Gromov say, tame this J. You see, if you have I will be considering some kind of analysis inside almost complex manifold, and then if J there is not this background symplectic form, then this J somehow misbehaves, and so really you cannot prove anything good. But if you have this omega which guards this J, then somehow everything fine, and as a result it turns out that in fact the result would be independent on J, but only dependent on omega. That's kind of what we philosophy. Okay, so this was about symplectic manifold. I come and tell you more later. But then let me kind of go down to dimension 3. So in dimension 4 I will be considering symplectic manifold and symplectic structure, kind of to help me with topology. And in dimension 3 I will be considering contact structure. The contact structure So, like, well, let's assume that this is a coorientable Xi, then it can be defined by some one form. This is Pappin equation, and then by Frobenius theorem, non-integrability can be just, well, what is the integrability? Integrability by Frobenius theorem means that the form d alpha restricted to Xi should vanish. But non-integrability means that this is never vanish. So that means that you, on each Xi you have a d alpha is area form or symplectic form. So what is the advantage of this kind of, in three-dimensional topology, really people looked at a lot of extra structure to start a stream matrix. For instance, one of the extra structure people consider which is very useful are foliations. So you consider stream manifold foliated by two-dimensional leaves. And foliation is precisely object when you get you have the tangent plane distribution to foliation is integrable. So it has a condition that the alpha equal to 0. And then you get this kind of structure. But then global topology of foliation is extremely complicated. Because, well, you have these leaves and you have this dynamics of these leaves, and really it's extremely sensitive to perturbation. So if you change a little bit, you get a, well, usually, sometimes not, but usually you get completely different topology of this foliation. And so it's very kind of much more much more difficult, I would say, object to handle. The context structure, like symplectic structure, has no local invariance. So that locally, even just contact form, not even context structure, but even contact form in some local coordinate system can be, for instance, always written in this form. You can always choose it for this Darboux normal form, or you can choose many other normal forms, but this is one of the possibilities. And so locally, there is no invariance. So this is not maybe so kind of, you say, so what? Because foliation also locally has no invariance. But most importantly, there is no global invariance in some sense. There are no continuous global invariants as well. Namely, if you have a family of context structures, so you have you deform your plane field, but in such a way that it keeps to be always non-integrable, always context structure, that all this family, in a sense, trivial. That means that there exists some isotopy of the manifold, such that if you kind of push forward, say, C0 under this isotopy, you get CT. So this is the theorem of Gray, and it just says that there is no deformation of context structure. Context structure is discrete objects, so you can kind of classify context structure discrete. And so, therefore, it's, in a sense, this, for instance, particular property make it, I would say, in some sense more useful in topology than foliation. So, now, let me explain what is the relation of, say, context structure and symplectic structure. The relation of context, on the first glance, this looks like different notions, but in fact, it's very close notion. So, like, if you take a contact manifold, and well, I will define it something non-invariant way, but you could do it also invariantly. Let's take this our three-dimensional manifold multiplied by R. So you get a formula, and here we have to say contact form, and then you can on this manifold say T the coordinates along this vector, and let's consider differential form e to the equal T alpha. So this is a kind of easy to check that this is a symplectic form on this manifold. So you have this cylindrical manifold. On this cylindrical manifold, you have the symplectic form, and this form, if you take a vector field d or dt, then this vector field is dilating vector field for this form. So namely, if you take a Lie derivative of omega along d or dt, then of course you get just e to the t. Well, actually you get just omega. And so therefore, just flow along this vector field, of course, just multiply omega by e to the t. So, and conversely, if you have a form manifold, and on this form manifold you have this symplectic dilating flow, then the space of trajectories of this flow is automatically contact manifold. And so there is a kind of, in a sense, you can formulate contact geometry as a projective symplectic geometry. So you have this kind of dilating action, and then kind of all notion of symplectic geometry, of contact geometry, can be formulated as a notion of this four-dimensional symplectic geometry, invariant or equivariant with respect to this action. So really the relation between these two is very close. So finally, I will meet one more kind of general notion, which we will be dealing with. This is a symplectic manifold with contact boundaries. Symplectic manifold with contact boundary. So what we will have say, four-dimensional symplectic manifold, and then you have a boundary which is a three-dimensional contact manifold. And then what does it mean? Of course, symplectic structure does not define any contact structure on the boundary, and it means some kind of condition in which sense they agree on the boundary. And the condition is there are two conditions. So first, well, you see, this xi you can define by some, let's suppose it's defined by someone, or alpha. And so one condition is the following, that omega restricted to xi is proportional to this d alpha restricted to xi. So you see, this, when I change form alpha, then the form d alpha will, on each xi will be just conformally changed. So it's conformal class of form d alpha depends only on xi, not of alpha. And so I want my symplectic form to coincide with this symplectic form d alpha on c up to this of some, not say, positive factor. So this is one condition, and then the second condition is some kind of orientation condition. It says the following thing: that if you have a symplectic manifold, then of course omega squared is a volume form. So therefore this manifold automatically oriented, and hence it defines some orientation on the boundary. But also contact structure knows its own orientation. It's also oriented. Because if I take an alpha wedge d alpha is a volume form. And notice that sign of alpha d alpha independent on sign of alpha. I can even change alpha by minus alpha, but still will be the same alpha wedge d alpha. So therefore, contact manifold knows its orientation. And so I require that this contact orientation with the boundary and symplectic should coincide. So it's two orientations coincide. Okay, so let me explain you what this notion means in terms of like complex geometry. I already told you for any symplectic form you can introduce this compatible J. So this omega will look like imaginary part of the corresponding quasi-scalar element. Now, you can choose this J in such a way that each xi, so you can choose J in such a way that each xi will be complex subspace. You can, this is also can be always done, that we have this manifold with contact boundary, we have this xi is xi is a complex tangent line to boundary. And then this condition, in fact, transformed to the following condition. So remember that omega of, say, of some v jv was positive. And then this kind of implies that this d alpha of v jv is positive for this contact form alpha. So for v in C. And then if you kind of know a little bit complex analysis, you know that there is a notion of pseudo-convexity. So in complex analysis, I will be kind of speaking Thursday more about this, but about this pseudo-convexity. But let me kind of in what few minutes today. So in geometry there is notion of convexity. And in complex analysis there is notion of pseudo-convexity, which is, from my point of view, much more fundamental than the notion of convexity. And this is this extremely bad thing that it was called this pseudo-convexity, and so it creates this kind of feeling that there is something really not so kind of good. So, but in fact, the pseudo-convexity is a really major, kind of more fundamental notion of convexity. So,
should switch it?
What?
Do you think it will cause confusion if we switch these two notions?
Well, we can try. So I'm sure there are some people who object. Okay, but well, you can. In fact, I will maybe there is a kind of another. I'm trying to polarize notion J convexity because it will be convexity with respect to certain complex structures. Call it J super convexity. Okay, super. Okay. So you have the super pseudo convexity, and now what it is. So, well, again, let's say, what does it mean in situ? What does it mean that hypersurface? So this is a notion about real hypersurfaces in complex space. So suppose you have, say, three-dimensional hypersurface, real hypersurface in complex space. Then it's called, say, well, even worse, not just pseudo-convex, but strictly pseudo-convex. So it's called strictly pseudo-convex if the following kind of true. That if you take so at any point you have in fact, tangent, you can take a tangent space to C, intersect with this ITC, and this is some plane, real complex line inside tangent space. And the complex tangent line to C. And the pseudo-convexity means the following, that if you can compute mean normal curvature of this hypersurface in the direction of C, then it will be positive. So, kind of equivalent definition is the following, that it's really convex up to geometrically strictly convex up to biholomorphic change of form. Or there is a kind of another characterization of it, the following. So how we can characterize convex surfaces? That you cannot touch convex surface from inside by geodesics. Right? Any geodesic, if you touch it from inside, it has to kind of go through. And the same holds for pseudo-convex hypersurfaces. You cannot touch it from inside, but instead of geodesic, by holomorphic curve. You cannot touch it.
Geodesic, you mean a straight line for the usual convexity?
Yeah, for the usual convexity in Euclidean space, or you are in Riemannian measure for the geodesic. But here you just substitute the word geodesic by holomorphic curve. Then it will be notion. Okay, anyway, so there exists this notion, and then it's precisely characterized by this property. So this is a notion of pseudo-convexity. This is one of characterization. It's just precisely like this. It's just essentially this mean curvature expression, and then it's called uniform, whatever. And so it just says that this, with respect to this compatible G, the boundary is pseudo-convex. So that's what convex boundary means. So in particular, what will be important, I will be considering holomorphic curve inside, and you can never touch the kind of maximum principle from inside this boundary by holomorphic curve. Okay. So I spent already for this introduction too much time, so let me deal with this. So what I will be kind of using, so let me just start to prove something. So I already mentioned homomorphic curve, and I will be this will be main object which I will be dealing with for all this my application. So you see, if you take a well, if you have a complex manifold, then locally you have plenty of holomorphic curve. In fact, locally you have plenty of holomorphic submanifold of even high dimension. But if you take a non-integrable complex structure, then if you try to find kind of complex submanifold of non-integrable manifold, you immediately found that as soon as the complex dimension of the submanifold is bigger than 1, then the kind of d-bar equation is extremely overdetermined. The integrability condition kind of really miraculously cut down this overdeterminacy and you get determined equation for any dimension. But if you go to kind of to generic non-integrable almost complex structure, then as well, you see it's in fact obvious. So we have you want to map k-dimensional real almost complex manifold, let's say complex structure J1, say JB, into another 2n-dimensional manifold with complex structure JW. And what does it mean that this is a holomorphic map? That means that the differential of this map should be a complex linear map between these two complex spaces. So what is the dimension of the space of this complex map? So you have so this is a k-dimensional, this is a n-dimensional. So real dimensions is complex dimension kn and real dimension 2kn. Right? And the dimension of all maps is, of course, is defined by 2k by 2n matrix, is 4kn. Dimension, no, what is it? Yeah, dimension is 4kn. So therefore, co-dimension kind of is precisely so therefore to define complex to cut complex homomorphic map out of all maps, we have to write 2kn equations. But you only have 2n unknown functions. So therefore, it's only determined if k is equal to 1. Otherwise, it's over. So therefore, you don't have a holomorphic submanifold of high dimension, but holomorphic curve exists kind of in as many in almost complex cases as in complex cases. You can talk. So this was known to classics, but they were existed in analysis by the name of quasi-analytic functions. And this was studied by Gecko and many people. But I think before Gromov, nobody really kind of realized that this kind of quasi-analytic function is the same as a holomorphic curve in non-integrable complex structure. Okay. So anyway, so you have this thing, and now you know that in complex manifold, locally, of course, you have a theory of holomorphic curve, but globally, you don't have this theory unless this manifold is scalar. There is no kind of meaningful theory of kind of global holomorphic curve, say, if it's a non-scalar manifold. And the same true in this case. If you take an arbitrary almost complex manifold, then, as I said, this holomorphic curve would not satisfy some compactness condition, so you really cannot define any good theory of them. But as soon as you have a symplectic structure taming them, then you have a kind of the same freedom of working with holomorphic curve in almost complex manifold, and even I would say more than in integral case. And this was a kind of first discovered and introduced by Gromov, and well, independently in some different way by some other people, but this is the kind of main contribution was made by Gromov. Okay, so let's return now to my situation. So let's kind of look at the following first question. So suppose you have a now four-dimensional, real four-dimensional, almost complex manifold. And this four-dimensional almost complex manifold again generically divided in two types. So one called elliptic hyperbolic point, another elliptic complex point, another hyperbolic point. So let me just not to give you now definition, but let me just kind of say that, for instance, if you take a, and this is a true up to some j, my definition. Suppose you have some R3 sitting inside my family, well, for instance, locally. And then this R3 is followed by complex lines. So now, if you have a surface, our surface sitting inside this R3, then this you get some kind of height function defined by this line, and I can talk about maximum saddle points of this function, then this and the maximum minimum correspond to elliptic point, and saddle correspond to hyperbolic. And up to some kind of higher order, third order, you can always find kind of oscillating R3 to any surface and define this as the same. Okay. So it was known in complex analysis, and it was explored by Bishop and by many others, the following thing. So if you take an elliptic point, and then near this elliptic point you always have a family of circles kind of converging to this point, such that each of the circles span holomorphic disk. Like in this picture, you have a family of this, you can cut by planes and get this holomorphic disk. Exactly the same thing locally through all. Now you want to ask, what happens globally? Suppose, say, you have only two elliptic points, and then you can have this local family emanating from this point, local family emanating from this point. Do they kind of meet, and how far they can be continued? And it turns out that in this situation, when you have a symplectic manifold or almost complex manifold with pseudo-convex boundary or symplectic manifold with convex boundary, and so let me just this is actually a theorem. So suppose you have some, say, symplectic manifold with such that with a convex boundary, and you have a J is a compatible almost complex structure. And then you have some two-dimensional sphere, say two-dimensional sphere contained in the boundary of this manifold, lying in the boundary. And suppose, well, this is actually not necessary, but let me suppose B has precisely two elliptic points and nothing else. Then S can be filled S. Then S can be filled with holomorphic disk. So what this means? That means that you have this Bishop family emanating from this point. They kind of continue and fill the whole sphere. And you know, automatically the corollary that all these disks that fill this holomorphic disk in that. So so you have our sphere, and automatically this all disk has to be disjoined and embedded, because you see they're disjoined and embedded near the top, okay, by local properties. But then intersection, if two complex lines intersect, they always intersect kind of positively. And so therefore index of intersection of two kind of topological index of intersections, or sum of indices of four intersection points, is always positive. And so it has to be equal just exactly geometrically of number of intersection points, because all of them positive. And so therefore, because it was zero at the beginning, and this is a topological characteristic, it has to be always zero. So all of them has to be disjoined, and by similar reason they have to be embedded. And so you always have inside, so therefore the corollary is that inside our 4-dimensional manifold, you would have a 3-dimensional ball collated by this holomorphic disk and bounded by this sphere S. Okay, so let me kind of tell you, this is already a pretty strong statement. I'll show you how this explore to get some kind of interesting topological consequences. So I would call context structure fillable if I will call context structure fillable if you can find symplectic manifold bounded by this context manifold. So okay, so let me kind of give a little bit about kind of background about context structure. So let's kind of let's consider two context structures on our take a say R3. So standard context structure is defined by this 4z minus y dx is equal to 0. So equivalently, this is the kind of equivalent you can in cylindrical coordinate write it by the 4dz plus r squared dθ is equal to 0. Just by changing coordinates is the same thing. So let's kind of look at the geometry of this context structure. This context structure this is a z-axis, and our contact plane is tangent to this radii, and they kind of rotate. And they rotate not much, they rotate by about pi, because dz over dθ is equal to r squared. So therefore, the never angle of this dz with respect to dθ is never more than pi over 2. Now, this contact condition precisely means that this you have to have a rotation in the same direction of any line. And we can consider different contact forms. You can write, for instance, let me write the following thing. Cosine r dz plus r sine r dθ. Let's consider this contact structure. So this would be locally the same contact structure, but then as we kind of go, it starts to twist and twist and twist. So let's see what is the property of this contact structure. So if you take a cylinder of radius pi, then on this cylinder of radius pi, our contact plane again horizontal. So the whole this cylinder, when you intersect with our contact plane, you will get family of horizontal circles. So if you take a small cylinder and intersect this contact plane, you get some spiral with a slope r squared. But then as you kind of go, then the slope eventually in this contact structure again becoming 0, and so you get horizontal tip. In particular, if I take a disk which looks like this, take this disk, and then look what our contact structure cut on this disk. What is the intersection? You get some one-dimensional fluation. And what you see, you get a kind of fluation kind of looking something like this. So the most important thing, so this circle would become limit cycle of this fluation. Notice that if our sphere, suppose this disk is a part of this sphere, and if this disk is a part of the sphere, then this fluation by this characteristic fluation never can have limit cycles. Because, you see, this is what kind of I was explaining to you. disk. And these two things has to be always transversal. And because it has to be always transversal, this characteristic relation cannot have, should be always transversal. Because if they are not transversal, then if two complex lines have a common real line, then they have to coincide. That would mean that this disk is tangent to the boundary from inside. And this contradicts the theory convexity. And so they always transversal. But if you have a relation transversal to this kind of simple fibration by this circle, it cannot have a closed leaf because this leaf would have to have a tangency point, maximum minimum. So, in particular, it says the contact structure like this never can appear in the boundary of the symplectic map. So, there is this kind of dichotomy of contact structure. Contact structure could be tight and over-twisted. So this is the example of over-twisted contact structure. Is a contact structure for which you can find such disk with this type of, with limit size. And so the kind of what I proved you, well, quote unquote proved, that I don't have to check, but essentially what I proved you, that if you have a contact structure which is a kind of symplectically fillable, then it always tight. It cannot be over-twisted. So the standard, for instance, contact structure on the sphere which bounds the standard round ball, it's always tight because it's filled by ball. Okay. So this is just maybe not so kind of exciting for you, but let me kind of give you now kind of more topological application.
So just to which one is the fillable? The standard one? Or
yeah, standard one is fillable. And this one is example of not. Because standard one is in fact can be, if you take a round ball and the standard symplectic structure round ball, then the standard contact structure on S3, which defined by really plane perpendicular to Prof vibration, is compatible with exactly.
And this is really, we have to think about it as the
yeah, this is dichotomy.
Half of them are like this.
Half of them tight, half of them over twisted. And there's I can tell you kind of a lot about this kind of dichotomy, a lot of things known about this now, but this would move into completely different territory. Okay, so, well, I think, well, time goes very fast, so let me just skip. I wanted play with more with this, but let me kind of give you, move to kind of some other application of the same thing. So let me prove you the following statement as application of the same circle of ideas. So take four-dimensional ball. Just round four-dimensional ball in situ, which is standard symplectic round ball. Now, suppose inside this two-dimensional ball, you have some two-dimensional disk, topological two-dimensional disk, embedded in this V4 with a boundary on the sphere. And we have the following property that this delta is symplectic disk, that the symplectic form on this delta is positive. And also that d delta is an unknown, for instance, is just a equation. Let's assume that is an equation. So we have the standard circle on the boundary, and it's bound kind of something inside. And this something inside is a topologically disk. So question, can this thing be noted or not? Is it kind of possible that this thing is noted? Well, for those of you who are not topologists, let me tell you that there are plenty of two-dimensional nodes in R4. There are as many two-dimensional nodes in R4, at least as many as one-dimensional node in R3. And so while a lot of noted disks. But now, question, can it be noted with this condition, that it's symplectic? and the theorem that it's not. The theorem that it's unknown. And let me prove it using the same type of idea. So you see, this disk on the boundary. So this boundary is in fact, so this is a S3, but this is a circle. This is kind of misleading picture. So in particular, this boundary bound there is some lower two-dimensional hemisphere which bound this circle S1 inside this bound. And this is just very round standard sphere. It has precisely one elliptic complex point here. So now I can always find almost complex structure, kind of compatible with omega, which is standard near the boundary, and for which this disk is a holomorphic disk. Because I just declare, you see, it's very easy to construct almost complex structure. I just declare each tangent line to this disk to be complex line. And because it's already symplectic, it does not contradict this compatibility. And so I made almost complex structure for which this disk is holomorphic disk. And then I extend it somehow inside. And then I start to fill it by holomorphic disk from this point. So I fill. Then at first complex structure standard, this is just a flat disk. But then they kind of become deviate, and what I claim, there is a kind of no choice for them as just to connect me the standard disk here with this, my original disk there. Why? Because, as I said, two holomorphic disks never can touch each other. So linking number of, or intersection number of any of these two disks is always 0. And eventually, this disk has to reach this one, because they're developing, so they don't have any choice as a kind of to reach this one. But as soon as it touches this disk, it has to coincide with it. And so you have a kind of the whole family of this disk, and this is a kind of isotope. So this is precisely, you see, what happens, this is a kind of indication of what happens. The symplectic topology is precisely kind of topology for like lazy topologies. Because in topology, people are kind of, well, develop extremely kind of inventive construction. So if you listen to real topologists, he would do some kind of miracles for you on blackboard, just converting one thing into another. And so, like mostly topology develop tools how to prove that two things are different. So to prove that two things are different, you need some invariance, you need some kind of complicated machine. But usually there is no machinery to prove that two things are the same, except just like by hand, just glue, and you have to really, it's really art, not science. But this thing, transform it into some kind of science, because what you really don't know how to make this isotope. By solving this Debar equation, by finding family of this disk, somehow you produce this isotope by itself.
Can you just point out where exactly you've been using effective omega on delta is positive?
Because I picked complex structure for this delta is holomorphic disk. And then my complex structure should be compatible. And main thing of compatibility is that omega should be positive on all complex directions. And so if from the very beginning omega was not positive at somewhere, I could not do this. Okay. So just another example of this type, I don't have time for it, would be the following. You can prove there is this self theorem which tell you that if you have any diffeomorphism at S3, then it always extends to the ball. And just there's an argument precisely like this which shows this. And in fact, so the original kind of, the existing proof is again extremely kind of complicated and elaborate. And this one, of course, it's used some analysis, but it just proved in few lines.
But you said any diffeomorphism of S3.
Yeah.
So to start with, you don't have any
by sphere, fill each sphere by holomorphic disk. And then take an image. This sphere become very complicated, but still they can be, on the boundaries they have still the same two elliptic points because the context structure the boundary didn't change. And then we fill them by holomorphic disk and then kind of using them we can understand. Okay, so one more kind of example of the same type, and then I spend -5 last minute to something else. So this kind of example can be generalized and pretty amazing from my point of view way. So let me define an invariant. I was a kind of against invariants, but let me still define an invariant of two nodes in an R4. So it's a pure topological question. So suppose you have some F embedding of two nodes at R4. So as I said, there are plenty of these two nodes. I'm not going to describe this, but there are a lot of construction how you can produce a lot of knotted spheres in R4. So I start with this one, and I will kind of using symplectic tools to define some invariant. So, and this will be the following. So you take this embedding, and the first lemma that you can always realize this embedding as follows. So this is a kind of theory. You can find some here. First, there exists some epsilon such that this F is isotopic to the following node. So you take a polydisk. You take a Stanford polydisk, which is a product of D2 of radius epsilon, and then I want D2 of some, say, fixed radius 2. So take this polydisk, and then I take on the boundary of the polydisk, I take a circle of radius 1. And then I consider some disk delta here, and this flat disk D here. So what I want to kind of present my Fs2 as a union of this disk D and delta. So I present my two nodes as made out of these two disks, like flat disk D and another disk in the complement of the polydisk, with the property that omega on delta is greater than 0. So I claim this is a kind of lemma that any node can be represented this way. So the second part of the theorem, that if, well, maybe I have to take here, let's take it 3. Take it 3. It doesn't matter. It's true with any number. So then, if epsilon is bigger than 2, then this F is trivial. So if you have a node realized in the complement of sufficiently thick polydisk, then it has to be trivial. So therefore, for any node, there is this kind of minimal thickness such that it can be realized in the complement. So you get some kind of invariant of the node. So what it is, it's kind of, unfortunately, I have some conjecture what it is for certain nodes, but no one computation was made.
So this invariant is a function of the number 3 that you wrote there?
No, it's not a function of number 3. Actually, it's irrelevant. It's not a function of number 3. It's in fact, I think that kind of the correct. It's kind of it's a function of some like in of the proofs, I would say. So I think the correct thing is number 3 is equal to number 1. So just I think you don't need to extend this. So this number 3 is only needed to prove the second part, and I need some. But I think that the number 2 still holds with 3 equal to 1. So it's, this part is actually relevant. I'm sure that only epsilon is relevant in this part. Okay, but you're right. This, as I formulated, it's function of number 3. Okay, so let me now say a few words about kind of other direction of application, just name, and of application of symplectic geometry in low dimensional. So I would say right now there are two kind of exciting projects going with relating to kind of, well, maybe more, but let me mention two. So kind of one secretly directed to disproving four-dimensional smooth Poincare conjecture, and the another one secretly directing to proving three-dimensional Poincare conjecture. But of course, the authors never say this. So, what is that? Let me kind of, this is four-dimensional project. So, this is the kind of the following idea. So, you know, when you take it, so I kind of first probably heard this idea from Gromov, but also, of course, many people, in particular Taubes, probably somehow came to this in the reality. So, you see, if you start with four manifold and you ask him, is it possible to make this manifold symplectic? Not any four manifold symplectic, of course, by the abstraction. But this is a hard question. But you can ask kind of a little bit, but you can always construct almost symplectic structure. Namely, you can do the following thing. You can let's suppose that omega has a, say, class, so it's cohomology class, such that square is not zero. So then you can, if you have a such cohomology class, which of course necessary condition for being symplectic, and if you realize it by harmonic form, this harmonic form automatically will be self-dual. So you can always find closed form, self-dual closed form with respect to Hodge operator, which realize this class. And then, for such form, if you take an omega square, it's the same as omega square, absolute value omega square, and this is always non-negative. So it's almost symplectic form, except these kind of places where this form omega vanishes. And generically, in generically kind of harmonic form vanishes along surface. So you always can construct symplectic structure away from kind of number of circles. Now, also you can prove that near this circle, you can have some kind of canonical form for this symplectic structure. There is two possible canonical forms. And if you cut the neighborhood of these things, you will get symplectic manifold with contact boundaries. The contact boundary will be S2 cross S1. But it will be not correct contact boundary. It will be different from my definition by the sign. So here is this kind of convex contact boundary, but this one would be kind of opposite orientation, kind of concave contact boundary. So now, in this manifold, you can now start to consider holomorphic. So now what you should do is the following. To attach to each such boundary S2 cross S1, attach kind of cylindrical end, like this symplectization. And consider symplectic structure which kind of invariant at this end. And there was a whole kind of theory of holomorphic curve in such manifold. It was developed by Hofer, and then also we have this what we call symplectic field theory, some kind of theory of holomorphic curve with such manifold which kind of asymptotically looks like cylinder over kind of some curve on this manifold. And then you can try to define what is called Gromov-Witten invariant for this manifold. So in Gromov-Witten invariance is something which counting holomorphic curve in the manifold. And in symplectic manifold, Taubes proved the theorem that this which relates this Gromov-Witten invariant is Symplectic invariant. So there is some counting way of computing Symplectic invariant, counting holomorphic curve. Now, for this manifold, the problem is that number. In this case, it's number. But in this case, it's not number, but it's kind of homology class valued in some kind of what we call contact homology of this over twisted contact structure. Well, it turns out that this contact structure turns out to be over twisted, unfortunately. And so, if you can compute, so just to produce this invariant, and there is some hope that, for instance, this invariant is non-trivial for some potential counterexample for smooth quantum conjecture, then if you can do this, so if you can prove that this kind of contact homology non-trivial, then you would get this invariant, and you can try to compute it. And this was so far was not proven. There is a kind of Taub's program which is doing this, and some other people kind of doing some parallel things. So this is a pretty kind of exciting area.
So to visit a potential counterexample to the smooth quantum.
Yeah. Okay. Let me explain how this related for example. So in fact, you can do it in slightly different way. So instead of working with 4 manifolds, you can delete 1 point. And if you delete 1 point, then you get a kind of, and now you kind of construct this self-dual form with delta charge, which would be kind of the same as constructing symplectic form, or self-dual form on M, which asymptotically look like standard form on R4. And here there exists a Gromov theory, which says that if you have a manifold, which is a asymptotically, symplectic manifold, which asymptotically look like R4, then this manifold is R4 up to blow up. So, therefore, if for instance, you started with symplectic with homotopy S4, and you delete 1 point, and you get this homotopy R4. And now you constructed this form, and then you have this circle. So now, suppose you manage to prove that this invariant, which is valued in this contact homology of this S2 cross S1, is non-trivial. That means that for this, because it's invariant, it's independent of the choice of this form. And so, if it would be possible to deform the self-dual form to get rid of the singularities, that would mean that this invariant had to be 0, because there's nothing to be valued. And so, therefore, if this invariant is non-trivial, so you cannot make this manifold into symplectic. But making it into symplectic is the same as making it in R4, because there is only one symplectic. So this is